Hi, there are many autonomous robots out there already, and many more are about to become available. So how do we make programming them easier, more efficient, safer, and more transparent? Let's first consider how this is done today and use the task of tidying up a room as an example task. First, we would need to consider what basic skills are required. Here we would need to pick up and put down objects, to navigate to them, and to detect them. We can either program these skills from scratch or use existing packages in ROS and other sources, or we can try to learn them using deep reinforcement learning, which is becoming popular recently. Now that we have the skills, we would need to write a controller that orchestrates them appropriately. Programmers do this today by implementing such a controller using a script or by designing a state machine. Now imagine that we would need to tidy up a whole house, take out the dog out, and do the laundry. To be efficient, the script must consider diverse scheduling options, various failure modes of each skill, and how confident it is about the information it gathered so far about the state of the house. A human is not very likely to be able to make all of these trade-offs optimally. Moreover, the actual behavior should be different for different houses, different user priorities, and more. So this approach of writing scripts is neither optimal nor scalable. Let's get a better feel for this through a simple example of programming the robot to play tic-tac-toe. We would need two basic skills: drawing a circle in a desired position and detecting the board state. Then we would need to figure out a strategy for using them to play well. And finally, we would write a script or a state machine that decides, based on the current board state, what to do. Now imagine we realize that the arm has difficulty drawing a circle in the center square, and if it fails, the turn switches. We need to rethink our strategy and rewrite the script to reflect the new strategy. And now imagine we're bored with tic-tac-toe. We need to play a new game in which you get points for drawing circles in the corners and near existing circles. This is a completely new game that uses the same basic skills, and we'd have to spend quite a lot of time thinking how to play it well, and then write a corresponding script. Now I think you realize how unscalable this approach is even in this simple setting. Every change in the robot, the task, or the environment requires us to reprogram the robot. And this is a problem with perfect information and almost perfect skills. So can we do better? So what about using all those fancy AI techniques? Well, many people would suggest using neural nets, deep RL, LLMs, which would miraculously solve our problem. But these techniques require training, which takes time. They won't take care of the nitty-gritty software engineering details involved, connecting all the components together, passing information, storing it, and so forth. Most important, these are not techniques that we can trust, control, or understand. Now, this may be suitable for game playing, but for more serious application, we would require the ability to control, trust, and understand what's happening. And this is going to even be required by regulations such as the EU's AI Act. I'll return to this later. So what do we offer? So in this video, I'd like to give you a quick overview of the autonomous operating system for robotics developed in my lab by my student Overtime with the help of Dan Suissa. Let's consider this idea of building up from basic skills and the example of cleaning a room. The basic skills that are required here, picking up, putting down, navigating, object detection, are typically imperfect. They can fail in various ways. The robot sensors too are not perfect, like people's sensors do not provide complete information about the world, and often they're noisy and inaccurate. So the challenge we want to address is how do we allow robot programmers to utilize existing robot skills to implement autonomous robots executing complex tasks, while taking into account the fact that skills have probabilistic outcomes, the robot has partial information and noisy sensing, and we often have diverse task requirements. And we want to make it easier and better than existing techniques. The AOS, the Autonomous Operating System for Robotics, is a model-based AI planning and execution system. What does this mean? It means that the programmers document their skills using a formal language. Now this certainly requires additional effort, but this additional effort can be greatly reduced using LLMs. And there's a high payoff. You document it once and you can use it by many users in many different contexts. Then the user describes the current task. Again, This can be done in natural language by an LLM that can translate it into a formal description. And now an AI planning algorithm takes over and uses this model to select which skill to apply when in order to achieve the task. Now, the AOS offers many advantages. The behavior is selected automatically. You don't need to write any code. It takes into account uncertainty in skill effects and sensing. So the algorithms can often optimize better than humans. It allows for rich task description, and when things change, one needs only modify the task or the skill description. You do not need to rethink and rewrite code. So this talk is intentionally non-technical, but behind the hood there are various important innovations which you can read about in the paper that's linked in the end of the talk, but let me briefly mention the key ones. The AOS is the only system of its kind supporting stochastic effects of skills, partial information and noisy sensing, and rich task descriptions. It makes no requirements from the skill code. This is very important, this separation, because it means that the developer of the skill code doesn't need to have the AOS in mind, and it could be, in fact, a learning algorithm. It also offers plug-and-play characteristics. This means that once you plug in a new skill with its documentation, the system can already use it without you needing to write any additional code. This makes incremental development very easy. It uses an innovative documentation language that is, on the one hand, very powerful and expressive. On the other hand, it's much more natural for programmers because it's based on the idea of generative models using probabilistic programming languages, which is just a fancy name for languages that also support the ability to sample events. And it also introduces an important concept of abstraction mapping for connecting the skill model to the skill code. Finally, it supports efficient sampling, which is very important for optimization algorithms. So, going back to the tic-tac-toe example, all the videos you've seen are of the AOS playing the game after Or and Dan provided it with two documented skills, drawing a circle and detecting the board state, and the task description, which is essentially what our winning position in tic-tac-toe, or in the new game we designed what are the scores received in different positions. No additional integration or programming effort was needed, and to adjust the problem for drawing in the center, a simple change to the draw skill documentation was required, and to adjust it for the new game, a simple change in the task description. And just to get a glimpse of these descriptions, this is the detect skill documentation with a few lines missing. This is the draw skill documentation. And this is what we call the environment file. It contains information about the starting position and the reward model. Here we highlight the changes needed for the faulty arm. So that's basically stating the probability of success and conditioning the next state on whether you succeeded in drawing or not. Here you see the description of the reward model for the new game. Here are some experiments conducted on a simulated world with a mobile robot with an arm. In this world, the skills can fail stochastically and the robot has imperfect information. No other current model of this kind, system of this kind, can model this environment. The task is to serve a can to a person on the left, and there are two tables, each with a can on it. The robot can navigate, can pick up a can, and can serve it over to the person. Navigate and serve always succeed, and pick can fail in two ways. The robot may miss it altogether, in which case it can retry, or it can fall on the floor, in which case the robot cannot pick it up. Now every action comes with some cost, and picking up the can at the top table is harder than at the bottom one. So what you see is how the robot behaves differently depending on its model, and you also see a nice example of the incremental development that's possible. On the left model, we do not differentiate between the success probabilities at different tables, and pick has a very noisy success sensor. So the robot tries to pick the can on the top table, which is closer. It fails, but it is not sure that this is indeed the case because it doesn't trust its sensors well enough. So it figures it's worth trying to serve the can, which it doesn't have, to the person, but because it is aware of the fact that it might have failed, it goes back, picks the can at the bottom table, and serves it to the person as well. In the middle, the pick skill success sensors was improved, so the robot immediately goes to the bottom table when it fails because it is more confident about the state. And on the right, the model is improved further by adding the information about the top table being harder to pick the can from. So the robot immediately moves to pick the can in the bottom table, and notice that such model improvements can also be done automatically by the robot through experience, right? So it can learn that one table is picking up in one table is easier than in the other. So what about LLMs, deep learning, and deep RL? As I stated before, I believe that we need AI systems that we can understand, trust, and control. Model-based systems provide this ability. We can understand the model, we can understand the optimization criteria, and we can understand how it is optimized. Still, LLMs are a great tool, as servants, not as masters. We can use LLMs to specify models using programmers' input in natural language and using their world knowledge. We can use LLMs to provide heuristics to help the optimization algorithm provide better solution faster. We can use deep RL and machine learning in general to improve model parameters based on experience to help solve the optimization problem. And by building models for learn and program basic skills, we provide a path to regulatory oversight. Basic skills are repetitive tasks we can better characterize, such as opening a door, pouring water, navigating, and so forth. So these are responsible and effective ways of combining the models we have and the optimization algorithm with generative AI and machine learning techniques. In summary, the AOS system was built to be used, not as a mere academic exercise. It drastically cuts down on the software engineering effort. There's no integration code you need to write, no scripts or state machines to write. You just document your skill code and you are set to go. The AOS empowers non-technical users because they can download documented skill code for their robot, specifies the task in natural language, and the system will solve the problem for them. You can see in the paper additional experiments showing the robustness and sampling efficiency of the system, detailed description of the documentation formats, and explanation of the conceptual and technical innovations. We are seriously looking for partners from industry who would like to collaborate on making the AOS the future autonomous operating system for autonomous robots. And you can see here a link to our paper and our emails, and we'll be happy to hear from you.